I'd just like to start by saying, Jasmine, thank you very much, well done, and you go girl. $200,000 instruments. The environment needs more investment like that. And in fact, listening to all the speakers so far, that's been the message coming through loud and clear. There's great work being done, but funding seems to be an issue. So we do need more investment. And unfortunately, I'm not going to diverge from that theme either, that what I'm going to talk about here will also involve some funding. Thank you. I really want to touch on benchmarking. Now, I've been working in the commercial irrigation sector, where we've got corporate growers who are all starting to ask more detailed ecophysiological questions about how much water do the trees or the plants that they're growing commercially, how much do they use? Because at the moment they have no reference, they have no information. Our state and federal research bodies don't actually have that information that they can use commercially. So I started to think, when I was asked to speak here, was, well, in actual fact, the same thing is true of the environment. In fact, it's probably even worse because we have such species diversity. We don't have all of that hard, empirical, objective, quantifiable data on basic fundamentals of plant water relations, plant water use. So what I'm going to do is just go through and see if we can cover the idea of how we might go about benchmarking ecosystem health. And the photo that I've chosen there relates to the work that's been going on for the last 14 years in California with the coastal redwoods. We've been monitoring those fundamental issues of plant-water relations in the 15 tallest trees on the planet for the last 14 years. And we're starting to really get some great information about how much water they use, why water is a limiting factor in the maximum tree height of this species, which allows it to grow to 115 metres tall, further than we can pump water ourselves, to other species that can only achieve, say, 70 metres or 30 metres. So good fundamental physiological questions that are being asked and answered over a very long period of time. And the point David Lindemeyer made earlier was the fact that we do need these long-term time sequence data sets, these long longitudinal data sets, which cover continuous data over a period of years, not weeks, not months, but years and tens of years. And hopefully I'll be able to show that we can do that, as we have been doing already for the last 14 years with Humboldt State University in California with the redwoods. So trees, to me, are really the proverbial canary down the mine shaft. And as Rhiannon Smith pointed out yesterday in her presentation, and put it more eloquently, that in fact the trees are really more the ecosystem health indicators. And that's what I'm trying to get at by calling them the canary down the mine shaft. Because when we start looking at the fundamentals of ecophysiology, go back to hard first principles of science, water is what drives the health of the ecosystem. And the trees allow us to monitor that because they are the most sophisticated sensor or transducer ever developed. We're still trying to replicate their energy capacities with solar panels. Trees have about 100% efficiency, solar panels have about an 8% efficiency. So we're still trying to catch up. This is the most sophisticated and elegant piece of sensor technology we have. And what that does is it integrates the 6 key abiotic variables in the environment. So the temperature, the light, the humidity, the vapour pressure deficit, the wind speed, the rainfall, the soil moisture, the nutrition, and then the biological components, the pests and disease. And again, as Rhiannon pointed out yesterday, a water-stressed plant or a water-stressed tree, as we've been looking at with the river red gums around Boggabri, it is far more susceptible to pests and disease than a tree that is not suffering water stress. So what these trees do is they integrate all of those environmental parameters, and they give us, if we're willing to ask and listen, they give us a continuous output of its assessment to utilise those resources in the environment to grow. So as I said, if we ask the plant and we listen to the tree will give us a continuous output of an ecosystem's health, because we are monitoring that fundamental parameter of water in the environment and how that tree is able to use and exchange that water for carbon dioxide to photosynthesise, produce energy and be healthy. So what we're looking at here, hopefully I can describe this on screen. I don't know if we have, oh yes we do, great. What we're looking at here on the top graph is we are looking at sap velocity. So this is the rate of movement of water through that tree, through the vessels, through the tracheids, whichever may be applicable to the species you're looking at. The movement of water through that plant. And we're looking at this over, And we're looking at this over a long period of time. So we're looking at velocity in centimetres per hour, and we're looking at time along the bottom axis. So we're looking at the characteristic diurnal curve, where during the middle of the day we typically reach our maximum water use, and at night time we typically reach our minimum water use. Now the two lines relate to radial positions in the tree, because trees don't use water at the same rate across the outer edge of the tree to the inner edge of the tree. So we measure at 2 points to get a more accurate measurement of the total water use going through the tree. Below that graph we then have the water stress. So we're able to continuously measure the water stress, or the energy that tree has to impart on the soil to extract water and use it for transpiration. So when we combine the two, we can see that in actual fact, and this is measured in megapascals and again over time. So we can see that at zero, we're at full hydration, the plant is suffering no water stress. But we need some level or some gradient, water potential gradient, in order to drive water through the tree from the soil to the atmosphere. So you'll see at night time we have our lowest water potential, and during the midday when we have sap flow we have our highest water potential, or most negative. And you can see that as the plant is using water, the midday peaks vary a little bit, and then we reach a dry point where the midday peaks continually dry down, day after day after day. And not surprisingly, so too do our pre-dawn, which is the first blue line, if I can find my red dot. No. The top blue line is our pre-dawn water potentials, continuously measured without the heartache of going to the field before sunrise and using a pressure bomb. This is while we were asleep in bed, nice and warm and comfy. The instruments were reading the tree and telling us how the tree felt. The second blue line is the midday water potentials. But you can see both midday and pre-dawn, both are declining the same as the sap flow rate. And I'll talk about that more later in a moment as to why that's really important to us for taking things to a landscape level. I'm sorry, but I think I'm out of juice. Okay, thanks. So this continuous long-term monitoring of the trees in the ecosystem, if we put a communications hub on there that has GSM or Wi-Fi or Bluetooth or satellite comms, we can actually send that data every 10 minutes straight back to the lab or straight to a mobile phone. So we can look at that in real time over successive years. So we can go back and compare data. We can also combine a weather station at that hub where we can multiplex, if you will, multiple trees and multiple species and look at the respective climate under which they're operating to give us a full picture of remote continuous environmental information about ecosystem health. We can then look at it online and look at the maps and look at each of the strategically monitored trees. So how much water does a tree use? Well, the coastal redwoods that we've been monitoring, they use anything from between 1,000 litres of water a day to anything up to 3,000 litres of water a day. How much does a Eucalyptus macrohinca use here at Armidale in the UNE Smart Farm? Uses 59 litres of water a day. The point I'm trying to make here is, irrespective of the tree and the size, they're going to use different amounts of water. So we need to be monitoring them. So that's what we've been doing out in the River Red Gums with Rhiannon Smith, where we've been looking at the large River Red Gums and trying to benchmark what is a healthy, well-watered, non-stressed River Red Gum tree. So we've been looking at them both on the floodplains and both on the riverbanks and looking at the difference between them. These are the big trees, as Rhiannon said. You know, they're quite difficult, particularly on the creek on the river to instrument. We've also had to look at the heterogeneous, the circumferential heterogeneity of the tree. It uses water at different rates around the tree. Just looking here, we can see that on the northern and eastern sides of the tree, which are the two top purple and blue lines, the tree's using the most water. On the western side, the green line, it's using half that water. On the southern side, the red line, it's using very little at all. So we need to account for that if we want to be able to measure the total water use of that tree. Once we have this information, we can then start to look at the total volume of water that's going through the tree and the times at which it's using that water. So we can see with the bottom graph here, this is litres of water per hour. So every hour we can see how many litres of water have gone through the tree, and we can actually interpret the environment through the response of the tree. Here we can see it's a beautiful sunny day. The tree is non-water limited. It is using water from the moment the sun hits the green factory right through the middle of the day at a very even rate right through until the sun hits the sunset. And then we can see it was still using some water at night. The next day, the climate's getting more variable. There's variations in sunlight. You can see variation. And then this day, you can see that as the storm has built up, it's rained, the tree hasn't used as much. It's used close to nearly the same peak of 6.5 litres of water per hour at its peak, but on the shoulders it's not been using as much because the climate hasn't required it to use as much. So we can look at the timing of when it's using water and the volume of water, and that's going to help us to understand and interpret the environmental and ecosystem health. We can also look, as David was talking about, longitudinal, long time set data. We can actually start to look at and compare the water use and the changes in the water use of that tree from season to season, from week to week, to month, to year to year. So we can overlay that data in real time via our interface. And we can see there that we've got the green line being a secondary period, which was a week after the yellow shaded period. And we can see that the nighttime water use between a week is very, very different. You can see that the second week we had a rainfall event in the mid-morning, whereas the week before we didn't. So we can start to read in a lot of environmental response by looking directly at the trees. I think I'm going to be asked to leave. Who wants me to leave? I'm doing pretty well, aren't I? This is interesting. No, you want me off, okay. All right. Should we give them a very quick option of a question, or should I just offer them the invitation? Okay, yep. We'll offer you the invitation to come and see me and talk more and more about this at 1 o'clock with the lunchtime demonstration in the courtyard. We've got some sap flow meters in the trees, and we can talk about it a bit more, and you can even have a play with them if you wish. So thank you very much.